And hello, everyone. Today I will start by explaining what exactly is fuzzing or fuzzy testing and why it is so helpful. Then I will have some quick diversion about Erlang. It turns out there's the main obstacle to fuzzing erlc. And then I will show the tools that I wrote for fuzzing all kinds of Erlang tools, including erlc and dialyzer and lots of others. And then the nicest part where I will show some of the bugs that were found and how and the kind of things it can find. So the idea of fuzzing is quite simple. It's to generate completely random inputs, feed them to whatever binary you're trying to test, and check that the binary doesn't crash and doesn't do anything else that is clearly wrong. It sounds so simple it could not work, but it found thousands of bugs in just about any program that ingests complex data. And compilers and static analyzers and so on are a typical example. There are two variants. The first one is to write a custom generator for whatever language you're targeting. So for example, if you're going to try to find bugs in GCC, you would write a random generator of C programs. The main cost of that is that, well, you have to do the work, and if you try to write a fuzzer for another language, you must do the work again. But it has lots of benefits because you can really customize your generator and you can test pretty much any binary. So there is no limits to what specifically you can test. The other approach, which is possibly more popular, is to use an off-the-shelf tool that generates random streams of bytes and gets coverage information from whatever is being tested to find what sequences of bytes goes deeper into the binary that you're testing. It's even more crazy because you might think that if you're generating random sequences of bytes and you're feeding them to, for example, an XML parser, you will never find anything. But thanks to the covered information, it will progressively refine the data that it is producing until it is producing valid XML, and it will actually find bugs. However, in our case, the goal is to fuzz lots of binaries like erlc, which is in Erlang, and eqWAlizer, which is in Scala, and the beam, which is in C. And so getting covered information from all of that in the right format is extremely difficult. So instead, I went with the first option because, after all, Erlang is a fairly simple language. So let's just write a tool that generates Erlang. So I said generate Erlang. What does it mean? The problem is that only a few Erlang programs trigger the bugs that we're looking for. So if we only generate a sample from a small subset of all valid Erlang programs, we are likely to miss the bugs that we're trying to find. If we are generating strings that are not valid Erlang programs, not only is it wasted, it is time that's not spent usefully, but it might be tricky to differentiate your program being rejected by the compiler, for example, as not being valid Erlang, and the compiler crashing. So our goal is to sample as broadly and uniformly as possible across all valid Erlang programs without generating code that's not valid. So what do I mean when I say valid? First of all, it should be syntactically valid. That's the easy part. Just follow the grammar. The second part is that whenever we are using a variable or using a function, it should be defined and you should be allowed to use it. The good news is that since Erlang is dynamically typed, it's fine if the code that we generate is ill-typed. It's actually somewhat good at times. because it tests like all of the exception machinery. That part seemed simple when I started this work. Like, how hard could it be making sure to only generate variables that you've already defined? Hopefully, I'll convince you that it's quite a bit more tricky than that. So here is a small snippet of code where we have a case expression, and we have a variable y, which is assigned to on each side of the case. And then we are using it on the two sides. So far, so good. The green y is the one that is defined in green, and the blue is the one that is defined in blue. No big surprise. What is a lot more surprising is that we can use y after the case expression ends, which I think is fairly well known in Erlang, but it's kind of unique because it means that things propagate outside of sub-expressions in some cases. And why this is valid, if we add another branch to the case, then suddenly it becomes invalid, because now there is a path that leads to this use of y, where y is not defined. Okay. Another thing which is well known in Erlang is that if you do y equal 42, this can be an assignment. But if you already have y, then suddenly it becomes an assertion. Which, okay, fine. That's a bit odd, but I can live with that. But then when you combine the two, you end up with examples that are a bit surprising. For example, here we are defining y on one side of the branch, not the other, and then I am doing y equals something. What does this do? Does this do an assignment, an assertion? Well, the erlc compiler is sane, so it just says no. I can't deal with that. So this means that when we're generating code, we must not just keep track of which variables are defined that we can use and which variables are free that we can define. We've got a third category, which is variables that are unsafe, variables that are defined on some paths but not all. And so we can't touch them at all, even to redefine them. Okay, another example. This code is a simple expression with two sub-expressions. Each one is perfectly fine. We are defining y. But the expression as a whole is not fine because the compiler can decide in which order to do these two assignments. And so which one should be an assignment and which one should be an assertion. So it will be rejected. However, if you have two sub-patterns, suddenly it's fine to have the same variable appearing for the first time on both sides. So whether or not you're allowed to repeat an assignment depends on whether you're within a pattern or within an expression. Okay, now for slightly more cursed things, you've got comprehensions. So what happens in this case? We've got the first x, which is in scope for the first generator. And then here, we've got shadowing. I just said that we don't have shadowing, we have assertions in Erlang. Well, that's an exception. And so now you've shadowed x, and you have a new x, which is used in the next generator, and then into the head. And then we're back to the old x, because everything that we did within the comprehension is discarded. And one small trickiness that while shadowing is allowed here, it's not allowed inside these expressions. So we can't just say like we are within a comprehension, shadowing is allowed. It's specifically in some places. And also, like if you define a new variable on the right side of a generator, it won't propagate outside of that generator. So this is invalid code. But if you do it inside a filter, it will propagate. So this is valid code. I will spare you the binary patterns and closures and other things. Just trust me that there are a lot of variants like that. So that's a bit depressing, but it's kind of possible to list all of the possible ways that that constructs in the language vary. So you can have shadowing or not. You can have an expression with a single sub-expression or several of them. If you have several subparts, you might be in an expression where you can't repeat assignments, or in a pattern where you can, and you have lots of variants like that. But you can kind of list them all and end up working through it. I don't have the time to go through all of the implementation details. If you're interested, you can either ask me after the talk or look at the code. So now I will do something very risky, which is a live demo. Hopefully it won't be a complete disaster. Right, so the tool is a small Rust program, and it has several subcommands. The simplest one is generate, which is only used really for testing it. It just generates a big Erlang program and dumps it. And so you can see it's not very readable. It's some fairly awful code, but trust me, it's valid Erlang code, including scopes. So you could just do this and then feed it by hand to tools, but I've slightly automated things. So you've got this fuzz command that takes as an argument the binary that you want to test. Instead of giving it directly programs, I recommend wrapping them in a small script like this. This is just a script that receives a program, feeds it to erlc, verifies that erlc did not crash, and then feeds the resulting bytecode to the beam and verifies that it does not crash, with a few things like timeouts and so on. And then you give it just a directory to put all of its crap, and another directory to put the actually interesting things if it found a bug. So as long as it does not find a bug, this directory will remain empty. And that's just the name to give the file. And so you can just do that, and here we see that it generated this file called foobar.erl, and it did not find a bug. Okay. In practice, you're not going to find a bug by running it once or twice, so you really want to run it hundreds of thousands or millions of times. The good news is that it does not have to be built into the tool because it's trivially parallelizable. So you can do something like this. Just generate a bunch of numbers, here for example from 1 to 100, and then call parallel to execute the previous command 100 times using all of the cores. And so if I do this, I'd get basically the same thing, but just going through the examples one by one using all cores. And it will soon reach 100, but you can do it with 1 million, and it will take a couple of days. So eventually, you find something that causes a crash. So you can look at this interesting thing, which I filled earlier, and you see that you've got some test cases that cause a crash, along with a standard error and standard out that was generated. These test cases are pretty nasty. Like, look for example at this. If I report this to like the Optimus P team, I don't think they're going to be very thankful to me. So I've added another subcommand to the tool, which is a bit too slow to show it in the demo, which is reduce. What it does is it will repeatedly call your script on the test case and eliminate small pieces of the test case. If the script still crashes in the same way, it will keep the simplification, otherwise it will discard it. And if you do that, then after like 10 minutes, you get something like that. And that is something that you can basically report as is to the OTP team or whatever other tool writers. Okay, so yeah. So I've told you that there is this tool. Hopefully you're convinced it is usable, but does it actually find bugs? And the answer is yes. It found more than 100 bugs so far. What I'm very happy with is that they've been fixed, and fixed quickly. So the teams responsible for all of these tools clearly find the bug reports useful and actionable. So how, what does these bugs look like? Most of them are just crashes. That's an example of one of the earliest bugs it found. This is a pretty small snippet of code, but it was enough to crash erlc. So one issue if you do things like that is that sometimes you won't see the bugs because erlc might completely misbehave but without crashing. So one idea is to make erlc and the beam crash more often whenever they're not behaving right. And the easiest way is just to enable assertions. And suddenly this found a new crop of bugs. So on this small snippet of code, if you don't enable assertions, the fuzzer won't find it because it appears to work fine. And actually it's doing complete craziness with a memory, and in debug mode it was easily found because there was some assert. A very similar idea is to use something like ASAN for address sanitizer. What ASAN does is that it checks all pointer loads and writes and makes sure that they're not out of bounds, they're not use after free, they're not double free, and so on. And similarly, this allows finding bugs in the beam that otherwise would be completely silent. I can't show you this particular test case because even the minimal one is a dozen lines, but that's still small enough to manage. And without ASAN, it was reading some null pointer and somehow was not crashing. And instead, it would just give you bad stack traces when you had exceptions. And with ASAN, it suddenly becomes loud. It becomes an actual crash, which we can report. So far, we've seen ways of turning things into crashes and then reporting them. But we might want to enforce slightly stronger properties of our tools than just don't crash. One example is that the tools should agree with each other. They should also agree with themselves across different versions and across different options. So for example, if you're compiling the same, So for example, if you're compiling the same program with erlc, both with and without optimizations, and then you feed both of these beam bytecodes to the beam, you expect to get the same results. And this example is a bit hard to understand, but the main idea is that you're doing trunk on an atom, which is not valid. So this will normally throw an exception, and so the whole guard will fail. And the Erlang compiler used to say, oh, this guard is dead code. It's always true, so I can remove it. And so it was returning A when it should return B. And this was found by comparing the output with and without optimizations. A very similar idea is to do the same thing, but at the beam level, comparing the JIT with the interpreter. If you're running bytecode and you've limited yourself to a deterministic subset of Erlang, then you really should get the same results whether the JIT is enabled or not. And the fuzzer found a few counterexamples, a few bugs in the JIT, where, for example, here it was negation that was wrong. Another trick that works well is just adding a timeout and saying that, well, if a tool like your compiler, which is supposed to be pretty fast, takes more than 30 seconds or more than 1 minute to compile a single file, something went wrong. There were quite a few infinite loops in erlc. Also some optimization passes that were not infinite, but that to try to rerun the whole optimization pass int max times, which is not going to end soon. So overall, here are a few numbers just for erlc, we see that we've got mostly crashes. We've got 4 issues that were found with timeouts. And then we get to the really nasty things, namely 3 cases where the compilation would appear to work just fine, but when you try to deploy your code, for example, hot code reloading, you segfault the whole VM, which is not great. And 6 times where you wrote code that was supposed to do something, and the compiler silently replaced it with code that has something else without telling you, which I obviously consider the worst case. One part that I'm rather proud of is that erlfuzz has started to be used on PRs before they are merged, and it often finds bugs when they're just 3 hours old and not 3 years old, and they're usually much easier and much faster to fix in that case. There were some nice side benefits of this work that were not targeted at the beginning. One is that while all of these scoping rules were not fully documented, much less specified, so I discovered them kind of by trial and error, and they got fixed and documented. It also found a few other corner cases. For example, if you had equality of patterns, so in Erlang you kind of some pattern equals some expression to match both. And if these patterns had binary subpatterns, sometimes the compiler would just refuse you, pretty much telling you this is not implemented, you've hit some corner case. And this was not exactly a bug because it would not crash, it would just tell you no, but it's still been fixed, which is nice. And Björn from the OTP team found some really clever trick to improve the code coverage of the compiler with the OTP test suite. He went through the compiler and for every line that was not covered by the test suite, he replaced that line with an exit. Then he ran the fuzzer, and it rapidly found a minimal test case of 1 or 2 lines that would trigger that exit. And this allowed him to enrich the test suite, and in many cases, like to discover, oh, why do we have this weird corner case, this optimization path? Oh, okay, it's for this kind of code. So I found this really quite cool. So to summarize, thank you. Okay, so the main takeaways are that if you have any kind of tool that ingests structured inputs, like a programming language, you really should use fuzzing on it, because it can find bugs even in 30 years old code quite easily. Doing it for Erlang is a bit tricky because of its scoping rules, but the work has been done already, so if you have any kind of tool that ingests Erlang, you can just get Erlfuzz from GitHub. It's open source and hopefully should be easy to use. And whatever fuzzer you're using, whether Erlfuzz or another one, you can massively improve its effectiveness by doing things like turning silent errors into crashes with assertions, sanitizers, and timeouts, and also by comparing the outputs of your tools with either other tools or other versions of the same tools or other options for the same tools. And these tricks are very general. They work on pretty much anything. Last but not least, I owe many thanks to the OTP team at Ericsson, and especially Björn and John, who fixed most of these like 100 odd bugs, usually within hours and sometimes within seconds of them being reported, which impressive. And I'm also grateful to my colleagues from WhatsApp who helped with fuzzing various other tools. Thank you for your time and for your attention, and I will now be taking questions.
Very cool. Thank you very much. So any questions in the room? Oh, a couple. All right. I'll start here.
Thank you for a very interesting talk. The variances and weirdnesses you found seems like unintentional weirdnesses that make it hard to fuzz programs. Do you think those variances come from faults in the Erlang BNFs or implementation?
As far as I can tell, the reason for all of this weirdness in the scoping rule is just that as each construct was added to the language, scoping rules for that construct were decided based on what's most ergonomic and intuitive for that construct in complete disregard for the rest of the language. And so they're not like each one independently kind of makes sense. It's just the combination that's a bit surprising and inconsistent.
Hey, this is a great talk. Thank you. So I was just curious, and this is, stupid question, but did you ever like collect cursed Erlang? Do you have like a cursed Erlang Hall of Shame?
I got a few cursed examples, but I used to work on C++, so Erlang is not that bad.
Yeah, so you said that equal sign can be either an assertion or an assignment, but isn't it always a match? So the decomposing match, right? So
yeah.
That's it's not. If you think of it like that, it's not really that weird, maybe. Or what's your comment?
I agree. It's not that weird, but from the point of view of generating code, there's a like I still have to treat differently between the definition of a new variable and the use of an existing one. So it's in that sense that I consider them different. I agree that logically they're one thing, but one changes the environment and the other just uses it.
So it feels to me that your fuzzing tests of the Erlang compiler are quite similar to, for example, what you do with property-based tests on your Erlang code. But I feel one big difference. Like here, you said you have to run millions of samples, and the program that you generated looked quite long, and it seems to be in sharp contrast with how we use Proper, for example, which in our case it's usually like every test run runs maybe 1,000 samples, which start from very small and then go up to still a quite limited size. So in your experience, what would you suggest how to set these sample sizes? So shall we, for example, at one time or during weekends runs 10 million samples for this fuzzing or property-based tests with very large sizes, or does this approach of starting with small examples and only thousands of them work?
So I agree that property-based testing and fuzzing is basically the same idea, just with different knobs turned one way or the other. The big difference is that property-based testing usually tests like a relatively small function or snippet of code, and it usually can check fairly complex properties of the output. Because we're trying to fuzz entire binaries, which are much larger, and most of our checks are basically, does it crash? We are much more limited. And so brute forcing things with lots of runs and big inputs is mostly a way to compensate for that. As far as how to use it best, in my experience, the way that fuzzing works best is that you have some of it running in the background, like every night, which is enough to find like the somewhat subtle bugs. and then you might want to run it for just a few minutes on every new PR, just to find the really big obvious things that trigger every like 100 runs. Because I said like 1 million, but most of the bugs were found much faster than that, within a couple thousand runs.
Yeah, other questions? Oh.
Hey, thanks. What OTP releases did you do the fuzzing work on? Like like if we're using OTP, which ones are safer?
I've started fuzzing the master, so trunk, back in, I think I started in July or August 22. So most of these fixes got into OTP 26. Some of them were sufficiently serious, they were backported to 25 or even 24. But yeah, it's mostly 26. You're welcome.
Can you control what type of output or what type of code the fuzzer is generating to test various things, or does it just generate random stuff?
So by default, it generates random stuff, but there are various options to tune that. So for example, if you want to test a tool that does not yet support maybe and map comprehensions, you can just pass a flag and it won't do that. Similarly, if you're doing the kinds of checks where you're verifying that code has the same output regardless of the compiler options, you have to pass a flag to reduce yourself to the deterministic subset of Erlang. If you want to control it more finely, you will have to patch the generator code, but it will be really quite simple because you've got, where is it? Yeah, you've got, for example, this kind of weights, and you can just set a weight to 0. So if you don't want to ever do a pattern matching against nil, you can just replace this by 0, and it won't have a pattern matching against nil. So it should be fairly easy to tune.
Another question? Oh, yes.
So it obviously gets asymptotically harder to find things over time, right? So how far do you think you are in terms of reaching a point where things are going to be becoming just infinitely hard to find things in phase space? Are you think you're 10% of the way there, or 90%?
Currently, it's no longer finding much stuff unless I improve the fuzzer in some way. So, for example, what I've got next on my to-do list is teach it to generate calls to ETS, so that we stress test that part of the beam. And yeah, that's the kind of thing. It's no longer in its original state where it was finding multiple things per day. Now it's finding like one thing maybe every few weeks. But every time I do some improvements to the fuzzer, teach it how to generate one new construct or one new kind of thing, it finds another batch of half a dozen bugs. So yeah. Thank you.